Planet Earth, a continuously changing, rocky ball of matter drifting in space. Time and upheaval have mixed the substances of the Earth into a vast number of combinations. Chemistry is the study of these substances and the way that they combine. A drop of rainwater is more than just water. A closer look and we can see, mixed in with the water, the tiny particles that maintain their own separate identities. And if we look more closely, we might see that many of these particles are themselves made up of other, separate, distinct parts. Like the drop of rainwater, these are mixtures too. Substances with parts that keep their own separate identities. Most materials in nature are mixtures. Now, a tiny water drop that is a mixture has found its way into a river, itself a mixture. The river flows past banks, mixtures of gravel and rock, sand and soil, vegetative matter and animal matter. These mixtures, picked up by the ever-flowing water, are added to the mixture that is the river. Living things are part of this mixture too, interacting with it, but still maintaining their separate identities. The river makes one characteristic of mixtures very evident. The proportions of the materials that form a mixture can vary. The mixture on the riverbed is constantly changing, and so is the shore mixture. The shore mixture washes into the river mixture, and both mixtures shift and change. A solid rock can be a mixture too. Bound together in this granite rock are bits of quartz and mica and other substances. Various samples of the rock show different arrangements of their parts. This is because the particles that form the mixture are irregularly spread throughout it. Even under the microscope, the thinnest slices can show this same uneven quality. Granite, like the other mixtures we've seen so far, represents a type of mixture classed as heterogeneous. The materials that make it up are unevenly mixed. Not all the particles that make up mixtures are visible. One substance in the river that's invisible is the gas oxygen. To fish and other living things, that part of the mixture is critical to their existence. And on land, living things depend on oxygen that is part of the mixture we call air for their existence. Oxygen, carbon dioxide, nitrogen, many gases form this mixture. Driven by the energy of sunlight, the process of photosynthesis takes place in the leaves of green plants. Within the plant cells, chloroplasts use carbon dioxide to manufacture food. And living things, even the simplest, use oxygen to convert food to energy. Humans depend on oxygen for the burning of fuel. Combustion operates engines, heats homes, runs industrial processes, and adds its own residue as a visible part of our atmospheric mixture. Water is also part of the atmospheric mixture, visible in the form of clouds or mists, rain or dew, or invisible as a gas, water vapor. The river mixture has some parts too tiny to see, parts washed out of the soil that floats with the river, and out of the rocks the river washes over. Eventually, The river pours its mixture of visible and invisible substances into the sea. The saltiness of the oceans is one result of particles in the mixture that are too small to see. If we take a tiny sample of the sea and let the water evaporate, then the invisible particles in the mixture cluster together and grow into salt crystals big enough to see. But when the crystals are mixed with water again, they dissolve. The water and the salt form a solution. A solution is a mixture, but it's different from the kind of mixture that granite is. Different samples of granite differ in composition. Granite is a heterogeneous mixture. But in a solution, the parts that make it up are evenly distributed. A solution is a homogeneous mixture. Every sample from a solution contains the same distribution and relative amount of materials. So, from a drop of rain to the vast ocean, we've seen this so far about matter. Mixtures make up most of the matter of the earth. Some of them are heterogeneous, with unevenly distributed parts, and some are homogeneous, with evenly distributed parts. Because the parts of a mixture maintain their separate identities, their physical properties can be used to separate them. Blood, for example, is a mixture of cells, plasma, and many other substances. A hematologist might want to separate out just the red blood cells from this mixture. They happen to be more dense than other components of blood, so that physical property can be put to work to make the separation. A centrifuge does it. Centrifugal force pulls the denser red blood cells out of their nearly homogeneous distribution in the mixture and concentrates them at the ends of the tubes in the centrifuge. Another physical property that can be used to separate the parts of a mixture is boiling point. Distillation makes use of that property. When a mixture contains one part that is a liquid, like the water in seawater, then we can simply boil that part away, changing it into a vapor, and then recondensing it as salt-free water. While only one part of the seawater mixture is a liquid, some substances, like crude oil, are mixtures of several liquids, and the ability of petrochemists to separate that mixture into its commercially important parts is the foundation of the multi-billion-dollar petroleum industry. The various liquids that are part of a crude oil pumped from the ground have different boiling points. The process that uses these different boiling points to separate the various parts of crude oil is called fractional distillation and is carried on at an oil refinery. This complex process that takes place at a refinery can be demonstrated in the laboratory in a simplified way. The mixture of liquids in crude oil includes gasoline, the jet fuel kerosene, and diesel fuel. And all these themselves are mixtures. The crude oil is heated. Each of the various mixtures boils off over a range of temperatures. In a fractionating column, the various parts of the mixture are separated. As the vapor of each part reaches the top of the column, it passes through a condenser and becomes a liquid again. The gasoline fraction condenses. The kerosene fraction. The diesel fuel fraction. And so a mixture can be separated by taking advantage of differences in the physical properties of its various parts. In our demonstration, the parts we extracted from the crude oil mixture were mixtures themselves, which could be further separated. But if we repeatedly distilled tap water, we would obtain a single pure substance: water. And now, we can expand the little diagram we started building before. Matter is composed partly of mixtures and partly of pure substances. The physical properties of a pure substance cannot be used to separate it into different substances. To separate a pure substance like water into its different parts, not physical changes, but chemical changes are required. One way to produce a chemical change is with electricity. If we pour water into an apparatus like this, we can force an electric current to pass through the water between the electrodes. And this time, the bubbling is the result not of a physical change in the water, but of a chemical change. Gases are forming at each electrode. One of the gases produced from the water burns. The other one doesn't burn, but it supports combustion. Of course, what we're demonstrating is the electrolysis of water, the breaking apart of water into its constituent parts of oxygen and hydrogen. The purpose? To illustrate that water is a compound. A compound is a pure substance composed of two or more different parts that cannot be separated by normal physical means, the way the parts of a mixture can. The smallest unit of the compound water is a molecule. We might represent a molecule of water like this. These balls represent the hydrogen atoms that make up two parts of the molecule. And this ball represents the single oxygen atom. If this is a molecule of water in rainwater, then this is a molecule of water in river water. And this is a molecule of water in seawater. They're all the same. Water, each with two atoms of hydrogen and one of oxygen. Every different compound has its own unique combination of atoms. In every sample of any compound, the proportions of the atoms and their arrangement are always the same. And so, you could describe any molecule of water as a hydrogen atom, an oxygen atom, and a hydrogen atom. Or, with chemical symbols and subscripts, by the familiar formula H2O. Like water, all compounds are composed of elements. Hydrogen and oxygen are elements, basic units of pure matter that cannot be further broken down or changed into any other elements by chemical means. And now, our basic breakdown of matter can be completed. There are mixtures, either heterogeneous or homogeneous, and pure substances, which are of two types: compounds and elements. Elements are the basic building blocks of all matter. Less than 100 different kinds of elements occur naturally on Earth, and almost always they are found in compounds and mixtures of compounds. Extracting the pure element normally requires chemical changes. In the case of iron, for instance, the heat of a blast furnace is needed to produce the chemical reactions that separate the nearly pure iron from its ore. Actually, purity of an element is usually not desirable. Other elements are usually mixed with iron to form steel, a more useful metal. Even after the element silicon has been processed to near purity, selected impurities have to be added to give it the properties we want. The controlled impurity of silicon in tiny semiconductor chips affects the properties of silicon and makes possible silicon's basic role in microcomputer circuits. Silicon, like every other element, has its own distinct properties. The properties of an element can be used to identify it. For instance, we can determine if the pure element gold is in this rock or if the shiny flecks are something else. They look like gold, but looks aren't really enough. A geochemist might compare the properties of a tiny sample with the properties of other substances, including gold. For instance, at what temperature does it melt? The sample absorbs a lot of heat, then begins to melt. The last golden flecks melt at around 1171 degrees Celsius. But gold melts at 1064 degrees. So the shiny flecks aren't gold. But we still don't know what they are. We can use a spectrograph to photograph the material's atomic spectrum. When heated sufficiently, the atoms of an element give off light that can be spread by a prism into a spectrum of distinct colors. This is a section of the spectrum of gold, iron, sulfur. Spectra are as individual as fingerprints, so they can help us identify unknown atoms. We place a tiny sample of the substance in the spectrograph. We'll heat it far beyond the point at which it vaporizes, until its atoms emit light. Then we'll photograph the spectrum of that light from our unknown substance. Here's a section of that picture. It doesn't match the same section of gold spectrum, but we were pretty sure it wasn't gold. Then what is it? Good guesses, or a process of elimination, would lead a chemist to these spectra: iron and sulfur. Together, they match our unknown substance, which, it turns out, is not an element, but a compound of iron and sulfur. Iron pyrite, sometimes called fool's gold. Now, although the elements iron, sulfur, and gold are quite different in properties, their atoms, like the atoms of all elements, are built of the same subatomic particles, protons and neutrons, found only in a central nucleus, and at various energy levels outside the nucleus, electrons. There's a unique composition of protons and electrons, plus a variable number of neutrons for each type of atom. Each atomic structure creates one particular element. The similarities in arrangements give certain groups of elements similar properties, and the differences give them different properties. For instance, copper, like most metals, has a luster or shine to it. So does the metal sodium. Copper and sodium share that property with most metals because of certain similarities in atomic structure. But sodium is much softer than copper because each element's unique atomic structure gives it distinctive properties. That's why the metal sodium reacts violently with water, while copper doesn't. Why copper is weather resistant, while iron rusts. And why many non-metals, like hydrogen and oxygen, are gases. And so, elements react chemically to form compounds like water. Compounds and elements, physically combined, form mixtures like seawater and rock. Elements, compounds, and mixtures form all the materials of our Earth, even the dynamic mixture that is life.